the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are ready for one of the largest theorems in all of linear algebra. Up to this point, you have seen quite a few theorems in this course, including this critical theorem list right here. You see that I have, like, for example, the existence equivalence theorem, which is mostly about the matrix equation AX equals B and whether there exists solutions to that matrix equation. Of course, there are some subtle non-matrix questions in here, or non-matrix statements. For example, a transformation maps Rn onto Rm means that the columns of the standard matrix A span Rm, means that for any vector B in Rm, the matrix equation Ax equals B has a solution. Those are three different types of conditions. One is to deal with transformations, the other is to deal with the columns of a matrix, and the last, which is the first here in this case, is to deal with the solutions of the matrix equation. In this video, we're going to tie those together, sort of, when we're only speaking about an invertible n by n matrix. We also had stuff like the uniqueness equivalence theorem, and this theorem is stated mostly about the homogeneous matrix equation Ax equals 0. It's centered on whether or not you have unique solutions to your matrix equation. So I hope that has been clear so far in this video series that really most of linear algebra is focused on two questions. Does a solution exist? And if so, is it unique? And then we had the existence and uniqueness of solutions to linear systems theorem. That's an oldie but a goodie. It just basically means that if the rightmost column of an augmented matrix for a linear system contains a pivot, then you don't have a solution. That's the existence part, that there does not exist a solution if the rightmost column in an augmented matrix is a pivot column. However, if it's not a pivot column, then you start talking about, well, we have solutions, so are they unique? And then that comes into the conversation about free variables. And by the way, that is sort of bled into both the equivalence theorems up above. And then you had a bunch of other theorems here, all these small little theorems that kind of creep into the background of linear algebra. And they continue forward as you look through here into our most recent theorems, which involve inverses of matrices and the uniqueness of solutions via invertible matrices. And as theorem 6 states here, some of the properties of invertible matrices as far as inverses of inverses and inverses of transposes and inverses of products. And probably one of the most important theorems, although not one we're going to be citing in this video, is theorem 7 there, which is that an n by n matrix A is invertible if and only if it's row equivalent to the identity matrix. That is super important because it allows us to find the inverse using elementary matrices and multiplying those against our matrix, or how we normally do it is via row operations on a system augmented with the identity matrix. Like this right here. You just perform row operations until the matrix A becomes the identity matrix, and what you get on the other side is A inverse. Because again, any sequence of elementary row operations that reduces A to the identity matrix also transforms the identity matrix into A inverse. Very, very important theorem. It's because, well, it allows us to find inverses, as I said before. Now that is all said so that we can jump into the biggest theorem in linear algebra, which is the invertible matrix theorem. The main point of this section is to bring together a lot of the theory learned up to this point in linear algebra and summarize the implications for square matrices. And that's the important part, for square matrices. This whole conversation has nothing to do with non-square matrices. It only has to deal with square matrices. And this note is exactly why I spent the first few minutes of this video just rehashing some old theorems. And if you've gotten this far in this video and haven't realized it, this is hugely important. This Theorem will glue together the existence equivalence theorem and the uniqueness equivalence theorem when dealing with square coefficient matrices. And it shouldn't be a square, it should just be square coefficient matrices. So all I've been is talk. What is the invertible matrix theorem? Well, let me just show you in a big picture first of all, so you can see it is a big theorem. It's a big equivalence theorem, actually. So what I've been calling equivalence theorems throughout this course are basically theorems that state these following statements are all the same. They all are either true or false. And that's exactly what the invertible matrix theorem is going to do as well. So really it is an equivalence theorem. Let's read through at least the first two sentences. Let A be a square n by n matrix. Well, that's a new rule. Up to this point, all of our equivalence theorems have been about non-square matrices, m by n matrices. Also, let's assume that A is the standard matrix for a linear transformation T. Then, as all equivalence theorems will state, the following statements are logically equivalent. They are either all true or all false. And you can see them written out here. I am going to talk about them in turn, but for right now, I just want you to kind of look at the glory of it. It seems like a lot, 15 statements, right? But actually a lot of them will be very familiar to you. I separate them into three groups: statements about systems of equations, statements that are about matrices and matrices only, because systems of equations statements can involve matrices because, well, you can transform or rewrite a linear system in a matrix equation. So I just want to make you aware that when I say these are statements about systems, these statements will still be centered around the matrix A. The matrix statements don't need actually a system associated with the matrix. These are just, what if I just have a matrix that doesn't represent a linear system? Somebody just handed me a matrix. What can I say about that matrix that would be a bunch of equivalent statements and then bleed over into these other system statements? And then finally, transformation statements. Well, transformations technically are very close to matrix statements. Actually, they're very close to system statements. However, transformations is a bigger topic, and so I like to have those separated out. All right, let's take a look at these. And again, they will seem very familiar to you. First one, for each B in Rn, and remember our matrix is n by n. So if it's a coefficient matrix, then we're talking n equations with n unknowns. Well, if somebody says, hey, no matter what I do, any vector I grab from Rn, ax equals b has a solution, then you know all the following statements in this entire list also have to be true. There's a little bit of a footnote on this, and this footnote is that technically the solution you're going to get for x, it will actually be a unique solution. However, the uniqueness of that solution is not needed to prove any of the remaining statements, so we don't clamp on that additional statement that it will actually be unique, just because it muddies up the proof a little bit. All right, what do we have next? Well, let's see. If S1, and I use S for systems, so if system 1 statement is true, then S2 has to be true. That is, for every single B in Rn, that B is a linear combination of the columns of the matrix A. That should be incredibly familiar to you again, because that's from the existence equivalence theorem that we stated earlier. Well, if that's true, then the columns of A must span Rn. And by the way, that's also from the existence equivalence theorem that we stated earlier. But here's something that wasn't in our existence equivalence theorem from earlier. The homogeneous equation ax equals 0 has only the trivial solution. Notice that I highlighted that in blue. That's because that is to deal with the uniqueness equivalence theorem that we learned way long ago. The equation ax equals b does not have a free variable. That again is part of our uniqueness equivalence theorem that we learned a while ago. However, when we stated it in the uniqueness equivalence theorem, it was the homogeneous equation ax equals 0. It does not have a free variable, but this is saying the same thing. And the columns of A should be linearly independent. Again, That is from the uniqueness equivalence theorem. So everything in blue is from the uniqueness equivalence theorem, and everything in yellow is from the existence equivalence theorem. By the way, I do not use these little letterings right here that often, probably will never again, but I just didn't want to have to write out all the wording. So this one theorem, the invertible matrix theorem, when you compress the matrix that you're talking about from being an m by n matrix, but instead being a square matrix, all of a sudden those two theorems squeeze together into the single theorem called the invertible matrix theorem. By the way, everybody calls this the IMT. Now let's talk about the matrix statements here. So all of those highlighted statements above we've had in the past. Well, let's see. A has a pivot in every row. I highlighted that in yellow because, you guessed it, it's part of the existence equivalence theorem. By the way, there is a footnote there. Since it's a square matrix, not only will it have a pivot in every row, but it'll have a pivot in every column, which makes it kind of an interesting condition. Because if you highlight that in blue as well, as the old commercial says, yellow and blue make green, having a pivot in every column is part of the uniqueness equivalence theorem. So that single statement kind of is bled in from both of those two theorems from the past. Now we're about to get into things that we have not seen in the existence or uniqueness equivalence theorems. And that is because those theorems were given to us well before we had the idea of an inverse. And so if you notice, most of these remaining statements say something about A being invertible. In fact, I will highlight the newer statements in pink. So if A is invertible, then all of those previous statements have to be true. You have to have a pivot in every row or every column, I should say, and every column, to be honest with you. Every single B in the codomain is the image of a vector from the domain. Well, that's a little bit ahead of where we are right now, but that's just basically this statement up here. For each vector B in Rn, Ax equals B has a solution. I just said it in terms of a transformation. Also, if A is invertible, the columns of A must span Rn. The columns of A are linearly independent. You could pick any of those statements. They will all be true because A is invertible. We have a theorem that we learned in our previous videos that says that A being invertible means it's row equivalent to the identity matrix. And that's where we get that guy right there. The next two, I could have written them as a single statement, but I just didn't, for a very special reason, because I had mentioned in a previous video that it is not always the case. If you see that you have, let's say we have two matrices, A and B, and if I told you that A times B is the identity matrix, it is not necessarily true that B is the inverse of A. It is true if A and B are both square matrices, but it's not true if A or B are not square matrices. So it's sufficient when you do have a square matrix, A, that if it is true that A times B is equal to I, then A is B inverse. And that's only true if you have square matrices. Essentially what I'm saying is, if you have a couple square matrices, it doesn't matter which way you multiply them. If that product comes out to be the identity matrix, then guess what? You found the inverse. And that's essentially what I'm saying here. If A is invertible, then there is a square matrix B such that B times A is equal to the identity matrix, and where B is equal to A inverse. And by the way, A is equal to B inverse. And same thing if you multiply on the right-hand side. Exists a matrix B such that A times B is the identity matrix, and B is A inverse, and A is B inverse. Again, we have a theorem that we just were introduced to, I think in the last video, that says if A is invertible, then A transpose is invertible. So all these pink highlighting pieces are just from a previous video. Going down to the transformation statements, if A is invertible, then the linear transformation x to ax is 1 to 1. And I highlighted that blue on purpose because that is from the uniqueness equivalence theorem. Likewise, the linear transformation x to ax maps Rn onto Rn that is from the existence equivalence theorem. And if I zoom out, you can see we've glued together pretty much everything from the existence equivalence theorem and the uniqueness equivalence theorem into this one single theorem. The final statement is that T is invertible, and because that's an invertible statement, it's not one that we have in our equivalence theorems, but the statement is if A is invertible, then the transformation is invertible, where A is the standard matrix for the transformation, and the inverse of the transformation is A inverse X. So there's a nice color-coded invertible matrix theorem. Everything in yellow, except for this stuff right here, everything in yellow is from the existence equivalence theorem. Everything in blue is from the uniqueness equivalence theorem. That green is from both of those theorems. And then finally, the pink is all kind of new inverse matrix statements that we've learned from our previous lectures in the past, maybe 1 or 2 videos. Little warning at the bottom here, the invertible matrix theorem applies only to square matrices. I've kind of said that enough, so I hope that that makes sense to you. Now here we are at the proof page, and this is where I usually go through and prove an entire theorem. But as you could probably see, the invertible matrix theorem has quite a few elements to it. However, to be honest with you, the proof is actually pretty easy. But also, any good textbook in linear algebra would have this proof in it. So instead of proving this, I'm going to justify a few statements here and there. I'm not going to go through all of them. There's no real need to. So the existence equivalence theorem relied upon our matrix being M by N. But if you trade out the letter M for N, the existence equivalence theorem should still hold. And so everything in yellow should be equivalent already. So for each B in Rn, Ax equals B has a solution, and yada, yada, yada. So those are all already linked together, and I proved those in previous videos. In fact, even this guy right here is linked in there. Moreover, everything in blue is from the uniqueness equivalence theorem, and those have all been proven to be equivalent statements. And again, that green is also linked in there. So all that stuff has already been linked together. Now, how are we going to link all the yellow and blue highlighting and green to the pink highlighting? All we need is one bridge, and that bridge is Theorem 5 in my textbook, which is unique solutions via invertible matrices. That's this guy right here. If A is an invertible n by n matrix, then for each B in Rn, the equation Ax equals B has a unique solution. It would be much better if this is written as an if and only if, but that can only be written as an if and only if you have a square matrix. If I told you our matrix was square, and I said the equation Ax equals B has a unique solution, I don't really care what the form of that solution is. All I care about is that the solution is unique. Then I know my matrix does not have any free variables. That means it has a pivot in every column. So again, if I told you the solution is unique, then it has a pivot in every column. Remember that green highlighting there is both for columns and rows for a square matrix. If it has a pivot in every column, it is row equivalent to the identity matrix. If it's row equivalent to the identity matrix if and only if it's invertible. So there's our if and only if link. That's our bridge from this yellow and blue and green text over to the pink text. And now we know it's invertible, so A is row equivalent to the identity matrix. We had a theorem earlier that we already proved. A transpose is an invertible matrix. And I'm pretty certain we proved this one, but I'm not 100% sure that T is invertible with the transformation inverse being A inverse X. If we didn't prove that, I apologize. But that's kind of a hand-wavy way of justifying the statements. Again, in your textbook, you should have a full proof. The proof is not terrible. I just wanted to kind of outline it because, to be honest with you, remembering all of this stuff is going to be challenging, and you want a nice, easy way to remember it rather than, oh, I have to prove it every single time. Now, I was going to save this for a different video, but I think that it's worthwhile to talk about a comparison of equivalence theorems in this video. So we have on the left the existence equivalence theorem, and that is for m by n matrices. In the middle, we have the invertible matrix theorem, that's only for square matrices. And on the right, we have statements concerning the uniqueness equivalence theorem. Again, that's for m by n matrices. Again, you could trade out m for n. So you could talk about square matrices in both the existence and uniqueness equivalence theorems. Just when you do that, they bleed right into the invertible matrix theorem. So in the invertible matrix theorem, for each b, ax equals b has a solution. It technically will be unique, but that's not required. Where is that born from? You can see to the left, it's born from the existence equivalence theorem. The second part of the invertible matrix theorem, for each b in Rn, b is a linear combination of the columns of A. Well, again, that's from the existence equivalence theorem. For each b in Rm, b is a linear combination of the columns of A. Again, you'll notice the difference here, because the existence and uniqueness equivalence theorems are based on m by n matrices, not n by n matrices. The third condition, the columns of A span Rn, well, there you go, the columns of A span Rm. We go to the fourth condition, and you see there's nothing in the existence equivalence theorem column. However, that's because the next three, S4, S5, S6, are born of, you guessed it, the uniqueness equivalence theorem. I'll highlight as I read, the homogeneous equation ax equals 0 only has a trivial solution. Well, there it is right there. The equation ax equals b does not have a free variable. Well, in the uniqueness equivalence theorem, it's stated that the homogeneous equation doesn't have a free variable. But if the homogeneous equation doesn't have a free variable, then nor does the non-homogeneous. The columns of A are linearly independent. Well, guess what? That's born of the uniqueness theorem. If you zoom out a little bit and erase all that coloring right there, you can see the next one comes from both the uniqueness and existence theorems. In the invertible matrix theorem, A must have a pivot in every row, but since it's square, that means it has a pivot in every column. And those are the conditions, although separate, in the existence equivalence theorem and the uniqueness equivalence theorem. When they get glued together, they just say there's a pivot in every row or column. It doesn't matter, they're the same number. And then we step into the invertible statements, which I talked about before. Everything I'm highlighting right now is brand new and doesn't come from those equivalence theorems. However, the transformation being 1-to-1 does come from the uniqueness theorem, and the transformation being onto comes from the existence theorem. So this little table here gives you a good visual of where we get a lot of that stuff for the invertible matrix theorem. It's essentially absorbing, it's like an amoeba, it just absorbs both of those equivalence theorems, only if you're talking about a square matrix. Now, I should say that a lot of people think this is only usable if you have an invertible matrix A, but that's not true. This is usable if your matrix A is not invertible as well, because once one of these is not true, they're all not true. That's what an equivalence theorem means. They're all either true or false. Now, there's not much else I can say about it. It's such a massive theorem that the best thing we can do is use it. And I'm doing that in a separate video. I just wanted to reserve this video only to talk about this massive theorem that hopefully you get enough experience with. You write it over and over again so that when it comes time for an exam in your class, you will have this information embedded in your brain. I hope that this helps you in your linear algebra course. Take a snapshot of the screen so that you might have a better organization for your material. And I hope you have a great day. Be a wonderful human.
It's the system of equations. Outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace.